Alright guys, today just making a little video to go over the study guide for our first exam. Let's see if we can do this in one take. So first off, non-calculator section, doing some limits. This stuff's pretty straightforward. Let's see. First one, limit x approaches 3, x squared minus 9 over x minus 3. If I plug 3 in, I'm going to get 0 over 0, so I know I need to do something else. So I'm going to factor here. Plus 3 minus 3. Difference of squares, that's easy. Right, the x minus 3's cancel, so this is the same as the limit as x approaches 3 of x plus 3, which is 6. Easy. For number 2, I know in class some of you guys had asked about this, and a lot of people kind of assumed that because we had 0 times cosine of 1 over 0, specifically the 1 over 0 part, we assumed that that would mean the limit did not exist. And I kind of mistakenly said, yeah, that's fine, when in reality we can prove that this limit exists. So I'm going to do it here. So if you think about this, we have x squared, so we have x squared times cosine of 1 over x. I'm going to think about cosine for a second. So I know that cosine bounces back and forth between 1 and negative 1 forever, correct? Cosine of x, right? So we know that the output, the range for cosine, is between 1 and negative 1. I'm plugging in 1 over x. That's not going to change the output for cosine. Okay? It's just going to change the domain for cosine. I can't plug 0 into it. It's going to change the shape of the graph, but it's not going to change the maximum and minimum outputs. So in other words, if I were to graph this x squared times cosine of x, it's never going to be greater than 1 times x squared, or I'm sorry, it's never going to be greater than 1 times x squared, and it's also going to be above negative 1 times x squared, right? It's going to bounce back and forth in between those values. So what I'm alluding to here is this is really a squeeze theorem problem. And we don't really have to worry about squeeze theorem that much anymore, so I would kind of ignore this one. I'm not going to put any squeeze theorem stuff on your test, but it is an interesting problem to think about. You know, if you have x squared, here's x squared, we know the shape of that. Negative x squared, just flip it upside down. Because cosine is bouncing back and forth between 1 and negative 1, we're multiplying that by x squared. What that means is we're going to be bounded by these two functions. And since both functions approach 0, as x approaches 0, that means that this limit is actually 0. So, kind of interesting. Again, don't worry about it too much. So taking a look at number 3, remember as x approaches infinity, I only really care about the biggest exponents on top and bottom. So if I just look at root 16 x to the 4th, that's a 4, over 4x squared, right? I can simplify that a little bit. So that would be the limit as x approaches infinity of square root of 16 is 4, x squared over 4x squared. Hey, that all cancels out to 1. Okay. Limit as x approaches negative infinity, 1 over cube root of x, or 1 over x to the 1/3. The top's not changing, right? Only the bottom is changing, and therefore our limit's going to be 0. Okay, so this limit approaches 0. Another way you could think of it, you know, cube roots, their result, you know, you plug in bigger and bigger numbers, you get a bigger and bigger answer. Cube roots grow very slowly, but they still grow. So you're getting bigger numbers on the bottom. 1 divided by a really big number approaches 0. Okay, I believe we talked about number 5 in class. So sine of x, We know it bounces back and forth between 1 and -1 forever. 1, -1, very accurate graph here. As we go out to infinity, right, we can't tell. We can't tell if we're at +1, -1, or somewhere in between. So we're going to say that limit does not exist. You don't have to say equals DNE. You could just say does not exist. Okay? Because of oscillation. All right, number 6, piecewise function. So we should take the limit as x approaches 2 from both sides. So as x approaches 2 from the left, let's call this f of x. That way it'll be a little bit easier to do the notation here. So if we take the limit as x approaches 2 from the left, that's just plugging 2 into this top part. So 2 squared is 4 minus 4, that's 0. If I take the limit as x approaches 2 from the right, or in other words, x approaches 2 from all the values that are greater than it, again, plug 2 in, that's the absolute value of 4 over 0. And number over 0, DNE. Okay. The left and right hand limits don't agree. Because of that, we can say that this limit as x approaches 2 of this function does not exist. Number 7, some continuity. Okay, so here we need to find k so that f is continuous for all x. So in other words, continuity, remember we want the limit as x approaches 2 from the right to be equal to the limit as x approaches 2 from the left. Okay, if that's the case, that means that the limit exists, right? We need the limit as x approaches 2 to exist, and we need that all to be equal to the function value at 2. So let's find f of 2 first. Okay. Here I see x less than or equal to 2, so I know that's the side I plug it into. So 3, let's see, 2 squared is 4, minus 1 over 4, or 1 over 2, I'm sorry. Okay, 12 minus 1/2. You could write 11.5 if you want. You could also say 23, 23 over 2. Either one would work. So in order for this function to be continuous, right, we need the left-hand limit to equal the right-hand limit. So I'm going to set the right-hand limit to be equal to 23 over 2. Okay. In order to make that happen, I need k minus 1 to equal 23 over 2. So do some quick algebra here. K minus 1 equals 23 over 2. Add 1. You get k equals 25 over 2. Or 12.5. If you like that better. Don't care. Next page. We did 8 in class, but we'll do it again. Remember, this is 7x minus 6, not b. That's a 6. Okay. Find a and b so that f of x is continuous for all x. So the way we can think about this is our function, right? On the one side, we have a piece of a parabola. Okay. So here's x is 2. I don't know what the output is. As we get to 4, 7x minus 6, that's the equation of a line, right? ax plus b is also just the general format for a line. We usually use mx plus b, but we're using ax plus b because why not? So that's what we have to fill in. We have to find the equation of a line. Now back in Algebra 1, you learned how to find the equation of a line. right? You had to find 2 points, and you had to find the slope. Oop, that's a y1. You had to find 2 points, or be given 2 points, find the slope, find the y-intercept. You're done. So that's what we're going to do here. So if we plug 2, right, that's my x1. Here's my x2. If I plug 2 in, I'm going to get my y2 value. So 2 squared, 4 minus 2, 2. Okay, so I know I have 1 point, 2, 2. Okay, find f of 4. Oh, I'm sorry. That's my y1. Can't count today. Let's find my y2, plug 4 in. So 7 times 4, 28, minus 6, 22. So there's my second point, 4, 22. Okay, so we're going to find the slope. Now, we usually use m, but in this case it's a, right? Rise over run, y2 minus y1 over x2 minus x1. Plug it in. 22 minus 2, 20. 4 minus 2, 2. So my a value is 10. All right, so I know I have a equals 10. I'm going to put this over here, just kind of hang on to it. Okay, now we need to find b. So we have, let's see, y equals 10x plus b. Pick a point. Plug stuff in. 2, 2 is probably easier to plug in, so I'm going to use those. So 2 equals 10 times 2 plus b, or 20 plus b. Subtract 20 from both sides. That will give us negative 18 for our b value. There we go. If you want to, you could always open up Desmos. Well, not on this, a test like this, because it's not a calculator. But if you just want to kind of prove to yourself, you can graph the piecewise function, make sliders for a and b, and then mess with them until the segment lines up. These are going to be the points that you end up on. All right, number 9, we have g is a continuous function. Okay, it's continuous everywhere. G of 1 equals 0 and g of 5 equals 3. So I do not know what it looks like, but I do know that at 1, let's see, and 5. Okay, so I know that at 1, I'm touching the axis, and I know at 5, I'm up here at the y value of 3. Okay, I'm not sure what's going on in between, but I know the function is continuous in between. Okay, so is it necessarily true that g of 3 has to equal 1.5? Well, it's halfway between the x bounds, so does that mean it's halfway between the y bounds? No, this says always true. Okay, it says always true. All right, the intermediate value theorem says that I have to touch every y value in between 0 and 3 because this function is continuous on this interval. Okay, that doesn't tell me what I touch and when. Okay, so I could go way up and down as long as I am continuous in between. So does this necessarily have to be true? No. Okay, could it be true? Right? If this was an always, sometimes, never question, you know, this is sometimes true, but not always. Okay, so it can't be choice 1. G of x equals 1.5 for some x between 1 and 5. Yes, that's exactly what the intermediate value theorem tells us, so that would work. Okay, thank you, IVT. 3, for all x between 1 and 5, g of x has to stay between 0 and 3. No, that's not the case, right? Think about our plane analogy, okay? I could go way up above and way down below as long as I'm continuous between. Lastly, for all x in between 1 and 5, there exists an x such that g of x equals 2. That is true. Okay, the IVT says that somewhere in between, I'm going to hit the y value of 2. I can't tell you where exactly. That's not what the IBT tells us, but it does tell us that it exists somewhere at least once. And I think that, oh, we got one more, and we're done the non-calculator section. All right, sketch a graph with the following characteristics. So I need the limit as x approaches 2 from the left to be equal to 1. Okay, so I'm going to put 2 right here. I need the limit as x approaches 2 from the right to be equal to 1. So let's say this is 1. This is 3. But f of 2 is equal to 3. Okay, so I know f of 2 has to be equal to 3. I'm going to put a dot there. Okay. However, because I'm approaching 1 from both sides, okay? I have to put a hole there and approach from both sides. I don't really care what's going on with the curve. That doesn't matter. I can't put a closed dot here because then I would fail the vertical line test. All right, for c equals 2, does the limit exist? Yes. Okay, it approaches the same thing from both sides. The limit is equal to 1. Right? Does f of c exist? Yes. By definition, f of c equals 3 because c equals 2. Is f of x continuous to c? No. All right, there's a hole there. Okay. And we could also say that the limit as x approaches 2 of f of x is not equal to f of 2. And that is the whole calculator or non-calculator section. Time for the calculator section. All right, have my calculator up here. Let's see, there it is. All right, so on the calculator section, anytime you're given a function, plug it in. Okay, so I have this ln, let's see, what is it? Ln of x, so let's see, y equals, we're going to do ln of x minus e to the x squared. So second e to the x squared. Make sure it looks exactly as it does written down, plus x cubed. Okay, so we're going to compute the average rate of change on 1 to 4. The easiest way to do that, again, with our calculator, would be to, because we have this set in our calculator as y1 equals f of x, we're going to use alpha trace. We're going to do y1 of 4 minus y1 of 1 over 4 minus 1. We'll do that in the calculator. Let the TI-84 do the work for us. Parentheses, let's see, alpha trace y1 of 4 minus alpha trace y1 of 1. Divided by 4 minus 1, tough one, 3. Gives you a pretty gross number. That's fine. Nothing wrong with gross numbers. So let's write that down. -2, what is it, like 2 million? Almost 3 million? 201. Gross. Okay. Negative. There's our average rate of change. Let's estimate the instantaneous rate of change now. So one thing I like to do when I'm looking at instantaneous rate of change, I just like to take a peek at the graph. So we're going to hit zoom 6. And there's our graph. Okay, I'm going to zoom in a little bit. And I can see that at, what is this, 2? Oh, it's outside of the window. This thing decreases very fast. So if you get a very large, very negative number, don't be afraid. I mean, your average rate of change was very large, very negative. So we could just do the exact same thing as we did before, right? For instantaneous, we don't know derivatives yet, so we're going to estimate. We'll just pick an interval that's really close to 2. So we do like 1.9 to 2.1, right? And because this thing is so steep, you could pick a slightly bigger or a slightly smaller interval, and your answer might be off by a lot compared to mine, and that's okay. We're estimating. Okay, so I just have written down here what we're going to put in the calculator. Okay. So, let's see. Second, quit. Clear out. Why is our calculator stuck? There it goes. So what I'm going to do, I'm just going to hit second enter. Okay. Bring this back up, and we're just going to change these numbers around. So, 2 second insert 0.1. 1 second insert 0.9. And the difference is not 3, now the difference is 0.2. Let's see what we get. Negative 214. Not as big as I thought. That's okay. Negative 214.006. If you want to round up to 007, that is totally fine. If you don't want to round up, that's cool too. You do you. Okay, so we're going to say negative negative 214.007. That's our estimate. And one thing you'll notice on calculator sections on tests is a lot of times you have less questions just because it's a little bit more time consuming. You have more stuff that you have to do in the calculator. Okay, identify all asymptotes and points of discontinuity. This really shouldn't be a calculator section question. I just made it one in case you are still uncomfortable. If you're still uncomfortable doing asymptotes without graphing. So horizontal first, that's easy. Okay, we have a bigger degree on bottom, right? So our function is going to approach 0. Okay, so we could say limit as x approaches infinity of g of x equals 0, or we could just say there's a horizontal asymptote at y equals 0. Vertical asymptotes, let's factor. Let's see what cancels. And discontinuities. If we do vertical asymptotes, we should also look for holes. So this equals, let's see, x minus 1. Multiplies to negative 6, adds to 5. So we're going to say x plus 6, x minus 1. The x minus 1's cancel. That tells us that there is a hole, not an ola, a hole at x equals 1, because that would make that factor 0. Vertical asymptote, well, all that's left over is x plus 6. So our vertical asymptote, if we plugged in negative 6, we'd get division by 0. So there's our vertical asymptote. That's it. You're done. That's all you got to do. Alright, particle moves along a surface according to the following table. What is the average speed of the particle? Speed, rate of change, between 3 and 13 seconds. So I only care about these 2 points, 3 and 13. Everything else is a distraction. Average speed, average rate of change, it's just slope, distance, over time. Plug it in. 50 minus 30. 13 minus 3. You get 20 over 10 or 2. Units matter though. Okay. We're going feet per second, so we're going to say 2 feet per second. It's a pretty soft calculator section, if you ask me. Evaluate the following limits. X approaches infinity of ln 2x squared minus 4. Again, put this on a calculator section because just in case you're not that comfortable with ln yet. But you don't need a calculator to do this one. We know that 2x squared minus 4, as you approach infinity, that's going to approach infinity. It's going to go on forever. And ln of x, the parent function, it very slowly approaches infinity. So in other words, the bigger number you plug into ln, the bigger result you get. So this limit is also infinite. Again, if you wanted to graph it, you totally could. You would get something that goes up as it goes left to right. Number 5, 1 minus cosine x over x. We have ways of proving this without a calculator, but we're not going to do that yet. So I'm going to bring this up, put it in y equals 1 minus cosine of x over x. Now is a good time to make sure you are in radian mode, not degree mode. Be a real shame if you were in degree mode. Always do radians. Let's graph it. Okay, so let's do zoom trig. Zoom trig's cooler. So as we approach 0 from both sides, our function is approaching 0. If you actually plugged in 0, you don't get an output. So that says there's a hole there. Doesn't matter to us. All that matters to us is saying that the limit is 0. All right, last question. Use the intermediate value theorem. So we're going to have to do something with continuity to explain why the function f of x equals ln x squared minus 2x has a root in the interval 2.1 to 4. So first off, I just want to check the domain. Check for any domain restrictions. For ln of x, you can only plug in numbers that are greater than 0. Okay, so for ln of x squared minus 2x, x squared minus 2x would have to be bigger than 0. Okay, so if we kind of solve this out here, then we get two possible solutions. We get x greater than 0, x minus 2, so 2, x is greater than 2. So I'm going to go ahead and graph it. Just make sure no funny business is happening. But what this tells us also is 2.1 to 4 shouldn't be a big deal. There shouldn't be any discontinuities there. Okay, so we know that f of x is continuous on the interval from 2.1 to 4. So we can use the IVT. All right. So let's go ahead and let's find f of 2.1 and f of 4. Our goal is to show that it crosses the x-axis. So maybe it starts up above and goes down below, right? That means that somewhere in between we have to cross, or vice versa. Okay, back to y equals. So let's see, this was ln x squared minus 2x. The natural log. That's what mathematicians use to start fires when they go camping. Let's take a look at the graph here. So I'm going to do Z-box just so we can get an idea of what's going on here. Because it looks like, okay, if you look at this graph, it looks like it's just kind of cutting off here. So let's see what happens when I draw a box. A lot of times your calculator will not do a great job of graphing the asymptotes for ln, and I think that's what's going on here. Okay, second trace 2.1. There we are. All right. No funny business. So this is another way you can plug in to, you can plug 2.1 in. So you could just do or you could just do trace, right? Hit trace, type in 2.1. It gives you the output right there. You could also alpha trace if you wanted to. Either way, it gives you the output. So negative 1.56. I'm going to write that down. I know you guys can't see that, but I'm writing it down. Let's see. It'll show up for you in a second. 0.5606, so 0.561. All right, let's take a look at second trace, or second enter. We're going to plug in 4. 4. The other endpoint, 2.079, or 2, yeah, we don't have to round up. So 2.079. Okay. And funny thing about this is, even though the question says, well, even though you have a calculator, so you could just look at the graph and say, well, here's the root, therefore it exists in the interval. It wants you to use the intermediate value theorem. So you don't actually have to find the root. I don't care about the root. If I wanted you to find the root, I would put directions in there that said, find the root. Okay. So what we're going to do is we're going to say f of x is continuous on this interval, and these two endpoints, because one's positive and one's negative, therefore f of c must equal 0 for some c in the interval 2.1 to 4. And that's it. Solve the problem. Good job. Proud of you. And hey, that's it for our study guide. Good stuff. Adios.